All right, guys. Today I want to make sure that real quick here as we start that we understand kind of the collective overall approach, and then hopefully we can start getting into some real hypothesis testing, some real situations. Yesterday, kind of started talking about what right-tailed, left-tailed, two-tailed tests were. Okay. Each one of these tests that we do, there will be a defined alpha. Okay. And remember, alpha was the probability attached to type 1 error, which is type 1 error is when we reject a null hypothesis that should not have been rejected. Okay. Meaning that we basically rejected a true null hypothesis, and we don't want to do that. Okay, so alpha is going to be something that you do not have to create. You do not have to calculate. It's going to be provided to you in the problem. Okay, if you were the researcher and you're conducting the entire study yourself, you would, before you do anything, you would think, okay, what is my scenario? What am I trying to study? And you would try to decipher what is the seriousness of type 1 error and type 2 error. And then based off of that seriousness, you will make a logical decision on alpha, okay, on what to use. We have here, I've got 3 normal distribution curves, okay, and basically show you what we're talking about here with what this alpha does and how we go about really conducting the actual test part of hypothesis testing. Okay, so right here, this is referred to in this first one. If alpha is 0.05, okay, the null hypothesis is the one that includes equality. So the null hypothesis says mu is less than or equal to 10. The alternative hypothesis, this one right here, that is the one that tells me what type of test this is, what tail it is, okay? And because it says mu is greater than 10, greater than means we're going to go to the right. So this is a right-tailed test. So that green statement right there is providing then this area right there that we're interested in. Does that make sense? Okay. So we want that area right there to be 0.05 area. Okay. Remember, the underneath the curve is totals 100%. So that area then is going to be 5%. Okay. So that area in the critical region, that's the critical region, that equates to the alpha level. Okay. The level of significance is what we call that. Is that okay with everybody? Okay. Now what we have to do is we have to find out what is the z-score that attaches to that. Okay. And here's kind of a picture of what's going on. Right here, ultimately, is our null hypothesis. If we put the normal distribution here, that's the location of our null hypothesis. Okay. And that is going to have a z-score ultimately, okay, of 0. Okay. Now, if that's the z-score of 0, all these other z-scores that mark our critical regions, okay, this one right here, this particular z-score right there that starts this critical region, if we develop from our sample data a z-score that is located at that red line or to the right, we will basically say that that is enough evidence to say that the mean that is found in the sample data is different enough from the hypothesized mean, which is h sub 0, okay, that, and it's so different that that difference did not happen by chance, okay? So basically what we're saying is that because it's so different, then we can't accept that null hypothesis as being the population mean. It must be something different. Does that make sense? Okay, and that will be, so if we get a z-score that falls over here, that will be enough to tell us that we reject this right here. And if we reject that, then it would support this idea here. Okay, does that make sense? So the way we find that score right there, that z-score, obviously we'll do this from the data that we get. Let's see here. Let me rephrase it. The z-score that will put us like here or here from our sample data, maybe it puts us here in the non-critical region. All that comes from our data, which we use x bar minus mu divided by sigma over root n, okay, which we talked about, and I'll write down again eventually. But to find this spot right there, you're going to use your inverse norm. Actually, it's norm.inv. Yeah, norm.inv. From Excel, we're going to type in the probability that we want. Okay, and because it's a right-tailed test, there's kind of two ways you can do this. Okay, because we have a right-tailed test, but the way that Excel and a lot of your other programs are built is that it's a left-tail cumulative probability. Okay, so if I want to find this red line, okay, what is the area of everything here that is white? 95. So I'm going to type in actually 0.95, and then it says what's the mean and standard deviation? Well, we want the mean to be 0, standard deviation to be 1. That's always constant. Okay, you don't ever change those to anything else. And when I type that in, it gives me 1.64, and that should be a number that we're comfortable with or we've seen in the past. Okay, so that right there would be a z value of 1.64. Is that all right? So anything to the right, so that right there is 1.64. So any z-score that we get from our data that would be to the right of that, okay, would be a value that would fall in the critical region. So that would lead to us rejecting the null hypothesis. Okay. You can also do it this way. Okay. I can just take my alpha. So we're in here. Take my alpha be 0.05. Hit enter. Gives me that, which is going to be the z-score that is right here. Does that make sense? Okay. And even though I want a right-tailed test, that z-score and this z-score here should be, because of symmetry, they should be the same except for the sign, right? So if I want to just type in the alpha and then just say, okay, well, it's a right-tailed test, so I know to use the positive version of that number. It might be easier for us that way. It's your choice. Okay, but that is going to be the critical value. Okay, that is, we go back up here to this vocabulary word up here. Okay, it says after choosing a level of significance, a critical value is determined using a table, and the value establishes where we have critical and non-critical regions. Okay, I know I really messed that up. I spelled where pretty bad there, but that's the idea of being able to locate critical values, and then obviously those critical values are the threshold for non-critical and critical regions, okay, which is ultimately then the threshold for whether we reject or not reject a null hypothesis. Okay, so on this one here, and actually let's just change this alpha level here so we see a different one than the 0.164. So let's go alpha is, let's go 10% here. Okay, so if alpha is 10%, but now we're looking at the alternative hypothesis to be less than 10. So because it's less than, we'd call it a left-tailed test. So we're going to have our area here, and that area right there, in this particular case, because of what my alpha is, that area is going to be 0.1. Okay. So I got to figure out, obviously, our null hypothesis is located here. we got to figure out what is that z-value, okay? Which, remember what the z-value tells you, that's how many standard deviations away from the mean we are. Does that make sense? And basically what we're doing here is saying, okay, if our sample data then is more than that many standard deviations away from the mean, then that is evidence to reject the null hypothesis and reject the idea that that is the mean, okay? But to find that, then we're going to go to our calculation. Now it's a left-tailed test. We want 10%, so I'm going to go 0.1 here, hit enter, and I get negative 1.28. So negative 1.28 would be that z-value that dictates the critical region versus the non-critical region. And in that case, because it's to the left, you would keep it negative. Yes. Good question. So this was a right-tailed test. It's a left-tailed test. This is going to be a two-tailed test. So in a two-tailed tests are the ones that always involve not equal to in the alternative hypothesis, okay? Because when it says not equal to, if H sub 0 is there, if my null hypothesis is right there in the middle, then in order to, because in a two-tailed test, we're just saying we're not equal to the mean is not 10, that's the argument here, then it could be something that is maybe the data shows that it was much greater than 10. Or the data shows that it was much greater or much less than 10. Okay, so it could exist on either end of the distribution. Okay, because we're just saying different. We're not specifying a direction. Is that okay with everybody? So when you don't specify a direction, it leaves it open to us having the ability to have a critical region there and a critical region there. Okay. And what happens then in those critical regions, we still have to abide by alpha being 0.05, and that is the total area of the critical regions, regardless of how many critical regions you have. And in this case, these critical regions, because of the normal distribution, they are symmetric. So that area right there is going to be 0.025, and that area there is 0.025 as well. Alpha over 2, remember that? Okay, so that's the same kind of thing we did with confidence intervals. Okay, so then on Excel, instead of typing in, bless you, instead of typing in 0.1, I'm going to type in 0.025, hit enter, and that should be a number that we're comfortable with. We've seen that before, negative 1.96. So that would be, this value there is negative 1.96. And that value there is positive 1.96. Okay, so as we take our data then, okay, and we run through the standardizing process for our data, if it spits back a score that is more negative than negative 1.96 or more positive than 1.96, then that will tell us that our population mean is not the same as what we're saying in the null hypothesis. So we would reject the null hypothesis. Okay, but if we landed in the white, we would say that even though the data suggests that the sample mean is different than the mean established in the null hypothesis, it's not different enough to say that the null hypothesis mean is not true. Does that make sense? Okay, because we've always talked about since day one that if we have a population and we want to know the mean of that population, let's say that we have, let's say we talk about the high school seniors and we say that we're going to do their ages in days. We've done that before, right? And let's say we're able, because the population is, I think there's like 120 of you guys, senior class. Okay, so we have that data. Okay, and we could actually find the population mean. And have that data. If I were to take a sample of 40 of you, okay, 40 seniors, and find your average age, it's not going to be the same exact number as that average of 120, right? Okay, And the difference happens because what we call chance, okay? Just because of the nature that the sample is not 100% the same as the population, then their values are going to differ a little bit, okay? But they should not differ by a drastic amount, okay? But in this situation, when we're doing hypothesis testing, that's what we're seeing, okay? If they understand that we know that sample means are going to be different than the population mean, okay? But how different, okay? And if they get too different, there's too much difference between them, then we make the argument, well, that could not have been the population mean then, okay? Does that make sense? All right, and that's all that hypothesis testing in regards to means is all about, okay? Now, if we understand that, okay, we have a structure then, and all we've got to do then is do one calculation, and that one calculation will tell us whether to accept or reject the null hypothesis. Okay, I say accept. I shouldn't say accept. Reject or fail to reject the null hypothesis. Okay, and the reason I think we use that wording is because when I say accept, I'm saying that it's true. Okay, but remember, because we're dealing with probabilities, nothing is ever proven 100% true, right? So we either reject it or fail to reject it, that terminology is arguing that we just don't have the data that suggests to reject it. Okay. So that's what, as you read through, we're going to skip some of these notes. I got these written out here for you in case you get stuck and need to go back and reference, that process that we just talked about right there. But that summarizes all of these notes right here in these pictures. Okay. Now, I've got this here to help you out a little bit. These are the common, and you can write these at, what I would do is I'd write these at maybe the top of my notes, or when I'm doing homework, and write them at the top of my homework, because those are constant. Those are always going to be the same. If I choose an alpha of, what to say here, 10%, and it's a left-tail test, that critical value that I get from my normal distribution is always going to be negative 1.28. It will never be anything else. Does that make sense? Okay, so if you want to write those down so that you don't have to grab Excel, you don't have to grab TI or Desmos or whatever, you can pull from there. Now, those are the ones that are most common for a left-tail test. Okay, now I could ask you, let's say alpha is 8% or alpha is 2.5% or something like that. We could change alpha, and then obviously it would change those. Okay, but those are the ones, and we go through all of statistics and all of the studies that have ever been done. Those are the three that are used the most. Okay, so it makes sense to maybe commit those values to memory. And that's it. That's for a left-tail test. So you see that they're all negative there, right? Okay. If I jump down to a right-tail, and I'll come back to this so if you don't have it written down yet. If I go to a right-tail test, are they the exact same numbers? Yeah, but they're what now? Positive. Okay. So right-tail test, left-tail test, those values are identical. Okay. For a two-tailed test, they're going to be different because for a two-tailed test, alpha needs to be split in half. Okay. So you're going to see completely different values for a two-tailed test. But the two-tailed test values that we see should be numbers that make sense to us based off of what we've seen with critical confidence levels, confidence intervals. Okay, if I go to a two-tailed test, for 10% alpha, it's 1.65. For 5% of alpha, it's 1.96. And for 1%, it's 2.58. And those are exactly the same z-values, z-scores that we were using out of confidence intervals. And you see there, in that case, if it's a two-tailed test, they are the positive and negative versions of those. Is it okay? Yeah. All right. Now, if we do enough of these, you're gonna probably commit those to memory. As we go through the process, I'm probably still going to use the calculator just to get in that mode to get you guys to see, okay, what if I don't remember these? How can I generate them? But you can just pull them off of that. that right? No, if you want to, so the critical value breaks our chart, breaks our normal distribution into either 2 or 3 regions. Okay? Here would be 3, here would be 2, right? And what's going to happen then is that we are going to, so this is the area then that is going to decide to reject the null hypothesis. Okay? So when we have data, and they might give us process data, so they might give us what sigma is, they might give us our sample mean, and they might give us n. And we'll run through our standardizing of that information, and it will give us a z-score back. Okay? We will then place that z-score somewhere on here, wherever it belongs on here. Does that make sense? If it is to the left of this shaded region that's over here, then that's going to tell us not to reject the null hypothesis. If our z-score lands over here, because it lands in that critical region, that will tell us to reject the null hypothesis. So the setup here is providing us a visual for us to make a decision about our data. Okay, so I think it'll make a whole lot more sense when we get to a specific example. Okay, so that's what I want to do now. Okay, this is here if you want to use it. It just basically lays out the steps for what we are going to do here. Okay, so it's find the critical values for specific alpha values using a table. If you want to use a table, I'm going to skip that because I don't want to use a table. I don't think you guys need to use a table. This is saying, okay, what do I do if it's a left-tailed test? If it's a left-tailed test, so we're looking at that area right there being alpha. Okay, I want to find that critical value that separates the critical and non-critical regions. So in that situation, we're going to take our normal distribution, take norm inverse, and we'll take point, because it's a left-tailed test, it's 0.1 here, hit enter, and negative 1.28 is that value. Is that okay with everybody? That's exactly how we'll do that. That'll be the first step that we do in all of our testing, is find out that value. That's the value that allows us to make a comparison to our sample data. Okay, so we need to be able to find that first. So that's a 10%, and that again, that negative 1.28 could have been something that you pulled off of left-tail test. We had alpha to be 10. There's your negative 1.28, right? Okay, so maybe you wrote that down already. The next one, okay, this is alpha being, it's a right-tailed test, is alpha being 12%. Okay, so we're okay with a 12% level of potentially having type 1 error. So if it's a right-tailed test, we're looking to find out what is the z-score that separates those two regions. So again, we're going to take our inverse norm. Okay, now you got two options. Okay, if I'm using this directly as a left cumulative distribution, then when it says a right-tailed test of 12%, that means the white area needs to be 88%, right? So you type in 0.88, and I get that number right there. Or, and this is what I like, because I know that the distribution is symmetric. So if I just type in alpha b 0.12, mean 0, standard deviation 1, just give me the same number but negative. So that negative is telling me that this z-score right here would be negative 1.7, but we want the one over here, so it's positive 1. I think it was 17. That kind of make sense? Okay. And if it's a two-tailed test, alpha being 0.02, then that area there is going to be 0.01. And that area there is going to be 0.01 as well. And then that is then the area that we type into our distribution, our inverse norm. Okay, so 0.01 gives me negative 2.32. Round to negative 2.32. 2.33, and this one will be positive 2.33. So every single problem is going to give you an alpha, and like I said, I'd probably say 99.9999% of the time, the alphas they give you are going to be 1%, 5%, 10%. Okay? But if for any reason they throw in a curveball and say 12% or 7%, that's how you would grab those values. Okay? Questions so far? All right, so let's do any problem. Before we get to the problem, these are the steps that every hypothesis test calls for. Okay? First, you're going to state the hypothesis. We've already done most of these. State the hypothesis, which is the null and the alternative, and identify which one's the claim, right? So we had an entire homework assignment that just devoted to step 1. Okay? Step 2 says design the study, select the correct statistical test, choose your level of significance, formulate a plan to carry out the study. Says the plan should include information such as the definition of the population, the way the sample will be selected, and the methods used to collect data. Okay, so that thing right there, step 2, you are in this class right now, you are not going to do that. Okay? But every single story problem that comes to us, okay, has that already been done. Does that make sense? So if we were the research group and we wanted to start from scratch, we would do that first. Okay? And that's what most of the class so far has been talking about. Okay? Techniques for sampling. Remember systematic, random, simple random sampling, cluster sampling, stratified sampling, that kind of stuff. Remember doing that? Talking about that stuff? Okay? That's how we would define it. That's how we're taking and collecting our data. Okay? We would decide our level of significance, and maybe we would, in our research, explain why we chose that level of significance. Okay? Because maybe type 1 error, the seriousness of it, and explain the seriousness of it. Okay? So that, a lot of that is going to be done for us. Okay? 3 says conduct the study and collect the data. Okay? So this is either observational study, where we're just, something has happened and we collect the data off that, or we go out and we actually hand out surveys, collect it, that kind of stuff, right? Step 4 says evaluate the data. The data should be tabulated, processed in this step. It says the statistical test should be conducted, and you decide to reject or not reject the null hypothesis. So step 4 is, process your data, okay? Put it into graphical tables, okay, so that you can read the data. Does that make sense? So it's no longer raw data, but it's processed data. Okay, and then step 5 is summarize the results. Okay, so that's how hypothesis testing is done. It says for purpose of this course, until a later date. Okay, so designing the study and collecting the data will be omitted, and the scenarios provided will already have those things done for you. So steps 2, 3, and parts of 4 will already be done for us. Okay, it says remember, in ethical research, researcher does not align their data with particular hypotheses, meaning, and we talked about this yesterday, if I am going to conduct a study, I probably have an interest in the results of that. But I want to make sure that I do not, when I'm done, align the results with the hypothesis that I established. Does that make sense? Okay, or my claims. That's unethical and can be very, very damaging. Okay. Another thing is, once we kind of talks about it here, once I collect my data and I run my statistical testing and that kind of stuff, and if it doesn't pan out the way I want, I don't go collect more data. Does that make sense? Okay. Again, that would be unethical. So we'll conduct initial hypothesis testing using critical values as described above. Our other texts will use a tool called p-values, which we will investigate as well after we understand the process laid out so far. Okay. This is just giving you an idea of what we're going to do over the next couple of weeks. So I'm going to skip that right now just because of time. Do you guys remember that flow chart I gave you the other day about, it was several weeks ago, about how we decide which type of tests or which type of confidence level to use, which table to use in our confidence levels, confidence intervals? The exact same chart is used here with the t-test, okay? Or the z-test, t-test, chi-square test, all that kind of stuff. Right now, what we are going to focus on where did my all right, we'll do this one example. All right, so state and local taxes. The U.S. average for state and local taxes for a family of four is $4,172. So a random sample of 20 families in a northeastern state indicates that they paid an annual amount of $4,560, with a standard deviation of 1590 at an alpha level of 0.05. Is there sufficient evidence to conclude that they pay more than the national average of 4172? Okay. Now, what I want to talk about here, okay, is let's say, actually, let's change this to, instead of 20 families, let's change it to 30. Does anybody remember why I need to change it to, why it has to be 30? Okay, so 30 says that the population is big, because in there, they're not telling me whether the population that it's coming from is normal. Does that make sense? Okay, so then I have to have a sample that's at least 30 to this. So I must pull this from a different section than what I wanted. But regardless, we can still do, if we change that to 30, we could do our hypothesis testing on that accurately. First thing we have to do is decide what our hypotheses are. So I'm going to say H sub 0 and H sub A. Okay, now because the only one that we've talked about, the only type of testing we've talked about is estimating the mean, right? Okay, or testing the mean. So that's our only choice. But if we eventually get to the point where we're, I give you 5, 6, 7 questions and they jump back and forth between different tests, you have to look for key phrases. So when it says average, that tells us mu is what we're trying to test, right? Okay, so we'll put mu in here for both these. Okay, now it says the U.S. average for state and local taxes for a family of four is $41.72. So when I see the word is, that's telling me the $41.72 should go in what hypothesis here? The null. And what type of symbol should I use? Equals. Okay, so equals 41.72. Okay, now as we read this, it says a random sample of 30 families in northeastern state indicates that they paid an annual amount of $45.60 with a standard deviation of 1590. It says at alpha equaling 0.05, is there sufficient evidence to conclude that they pay more than the national average of 41.72? So if they pay more, then we'd be looking at this, correct? Does that make sense? And the way that this is worded with questions like this, because nowhere does it say that a researcher reports or an individual claims or anything like that, right? So at that last statement where it says, is there sufficient evidence to conclude that they pay more? That wording tells us, and it's going to be consistent all the time, that wording tells us that this is indeed the claim here. Okay. Now, we talked about how, these two things need to be contradictory. They need to be opposites or complements, right? Okay. And they're not, okay? But we did have a statement earlier that said some authors, some research will always use equality here and then use inequality here. But if we want to stay with being 100% opposites of one another, I would have to put less than or equal to there. Does that make sense? But it's not, to be honest with you, it's not a big deal. Okay? But those are our hypotheses. Is that okay with everybody? Okay? So now, if alpha is 0.05, and this is greater than, what type of test is this going to be? It's a right-tailed test. Okay? So I'm going to come over here. I'm going to have 0.05 there. That's my alpha. So now, when alpha is 0.05, that gives me negative 1.64, but it's to the right here, so it's actually positive 1.64. That's that z-score. Okay. Now we have everything set up the way we need. Now we got to look at our data. Okay. And to find our z-score right now, we are going to take x bar minus mu, this will be the same formula until I tell you otherwise, x bar minus mu over sigma divided by root n. Okay? We've seen this before. X bar is your sample mean. Did they tell you what your sample's mean was? $45.60, right? Minus mu, well, mu was established in our null hypothesis as 41.72. Standard deviation, 1590. That's sigma. Divided in by the root n, which n was 30. Okay? So now if I go ahead and calculate that stuff, so I'm going to do it in Desmos real quick. We'll take 45.60 minus 41.72. We'll divide that whole thing by 1590 over the square root of 30, and it gives me 1.33. 1.34. Is that okay with everybody? Okay. So where does that 1.34 lay in comparison to this 1.64? To the left. It lays about right there. Does that make sense? Okay, that would be a z-score of 1.34. Is that in the critical region or the non-critical region? That's in the non-critical region. So because it falls in the non-critical region, we would say we now fail to reject the null hypothesis. When you land in the white area, you fail to reject. Okay? Which tells us, data-wise, from our sample, even though our sample mean of 4560 was different than what our population mean was hypothesized as, right? But what we're seeing here is that was not different enough to say that the mean of the population is not 4172. That kind of make sense? Okay? And the idea is that this 4560 was from chance. Okay? Maybe one of my sample of 30, maybe one of those guys in there was a millionaire. Does that make sense? And it bumped that up a little bit, but that's just chance that he got added into that 30 families. Okay? No homework tonight. Have a great week, and tomorrow I'm going to post something. I'm going to grade it as a quiz, but it's going to be set up like a homework for you to work on tomorrow. It'll be due tomorrow, too.